It's great to be here, even though I'm actually not technically officially here. I was out here visiting for the week, and it's always a dangerous thing when you visit Berkeley, because Umesh could always run into you and force you to end up moderating a panel. Umesh had only one request out of me, and that request, if you know me, is highly unlikely to be observed, which is he asked me to let other people talk. So I'll try to do that as a moderator, despite my reputation. But in any case, it's my real privilege to have a great panel of folks here who I hopefully will let talk. Actually, I'll let you guys all introduce yourselves. So please, go ahead.
So I'm Jiaqi. I'm a postdoc here. I'm mainly working on Hamiltonian complexity and the potential quantum advantage for quantum chemistry.
Hi, I'm Robbie. I just finished my PhD at Caltech, as well as, along with Jiaqing, and currently I'm unemployed, but soon I'll be starting a position that's joint between Google and Berkeley. So, yeah.
And I'm Martin, and in the chemistry department here, and work on computational quantum chemistry.
Wonderful. Thanks a lot, everybody. So I think, all of us, of course, have a really strong interest in quantum chemistry. So one of the things I guess I wanted to ask to begin with is, from all of your perspective, what's the thing about chemistry that you're most excited about, or quantum chemistry simulation you're most excited about at the moment?
You mean specific question, or like a specific problem, or? Whatever,
man.
So Fermi-Hubbard model?
I'm sorry?
So design quantum algorithm for Fermi-Hubbard model. I think the exciting part is because, it's because people told me this is toy model to understand room temperature superconductor. So I think that sounds a very fancy thing. Yeah, and very exciting to talk about it.
And so what would you like to study about the Fermi-Hubbard model in particular?
So in fact, in my morning's talk, I'm mainly talking about ground energy, but according to my discussion with chemists, physicists, I think I think the main question which seems very hard is to estimate certain local observable of Gibbs states. Yeah, for thermal states. For example, when you're talking about high temperature or room temperature superconductor, it's not ground state. So so ground state is relatively easy in classical simulation, and the Gibbs state is much harder. So in summary, I'm just saying for Hubbard model, you just you want to the special question is you want to design an algorithm which can efficiently prepare low temperature Gibbs states, and then calculate certain observable values green function, something like that.
I'm excited for the glorious quantum future where we're discovering crazy, strongly correlated materials and putting them out into the world.
Are you sure you're not working for a company?
And I guess I got into this because I want to know what electrons are doing in molecules, and I continue to be excited by that. And as a professor, I should be excited about what everyone in my group is doing, and I am. And since Avijit is here, I will represent the piece of my universe that overlaps with him and say that I'm very excited about improvements in embedding theory and how they may inform the future of quantum simulations.
So is it fair to say that you're in a strongly correlated excited state?
Absolutely.
Great. So I guess one of the questions that I wanted to ask is about the prospect of showing advantage for quantum chemistry simulation. There's a number of things, both positive and negative, that have come out in recent years. One, of course, has been some of the surprising successes of DMRG in order to be able to simulate relatively large molecules, as well as actually somewhat negative results from the classical perspective from Hamiltonian complexity. I was wondering if you guys could tell me what the state-of-the-art understanding of where the challenge barrier ends up lying.
I mean, in terms of Hamiltonian. So, do you want to begin with Hamiltonian complexity or classical heuristic?
Well, we've got a wide crew of people here, so there's two ends to this thing.
Yeah, so I think from Hamiltonian complexity perspective, as I said in my talk, I think I would advert advertise like people to working on like some more specific Hamiltonian. So okay, in particular, I feel also if we're looking for quantum advantage, looking for tractable case, I feel most Hamiltonian you can come up with in the qubit case is really QMA hard. So I think if we're really looking for like a tractable case, I will encourage everyone to learn fermions and start looking at fermionic Hamiltonian.
Okay, so I'm going to give quite a long answer to this question, if that's okay, and then maybe
I'll shut you up if you get boring.
Okay, so I mean, the truth is that chemistry is not a solved problem, right? Like there is no AlphaFold for predicting electronic structure, right? Like if chemistry was doable classically, then such a thing would exist. So people believe that chemistry and physics problems are difficult, otherwise they would be solved. But then, so the question is, what can we do to sort of assess the abilities of quantum computers to help with that problem? And something I would like to see is the following. So, I think a lot of work in this area sort of focuses on worst case sort of complexity theoretic analysis, and to me that doesn't really inform on this question too much. And something I would be excited to see is, okay, so suppose we take it seriously that chemistry and physics is difficult for classical computers, sort of somewhat generically, and that quantum computers should be able to help. Then it should be possible to do the following. It should be possible to write down a well-defined toy model, a well-defined model. So you write down, here's an ensemble over Hamiltonians or over physical systems or something, and here's a question that we want to ask about it, like compute this physical quantity or something, and then you can write down a quantum algorithm which does that, and then we can start to try to do it classically, and then hopefully it will be hard, right? So to my knowledge, that no such thing currently exists, but I don't see why not, because if it's true that quantum computers have advantage, then we should be able to find such a model, and then such a thing would really help with our understanding, I think, because it would do two things. First of all, you could try and strip away all of the actual sort of details that I don't understand, like all of this chemistry details and stuff, and just have a very well-defined, clear theoretical model that a theorist can analyze and prove theorems about, ideally. So that's the first thing. It would be like sort of simple enough to analyze. Second, it would sort of hopefully give some insight about where to look in the real world. So where to look, which kind of physical systems do we expect to see the biggest quantum advantage? So suppose, maybe like you wanted to have a sign problem or to be strongly correlated or something. And ideally this model would sort of have that in saturation. It would have like the most sign problem possible or something like that. And then the third thing that this would probably do is it would probably be the cheapest thing to run as well. So it would be the first thing we would do as like a demonstration as we start to build fault-tolerant quantum computers. So I think that's a direction that I would like to see personally.
Well, I think there's a pleasing degree of uncertainty about the exact status right now. Again, as a quantum chemistry software developer for classical computers, we have something like 50,000 users around the world who are doing things and trying to solve problems right now, and they would like higher accuracy, and they recognize that there is a class of problems, these strongly correlated problems, where the answers just don't agree well with experimental information. So therefore, it seems that pushing on those two topics from a completely heuristic point of view, i.e. where a classical method stymied, seems productive for the future of quantum information. And at the moment, it's really about making arguments about near-term scaling experiments and how they will translate to hopefully the the exponential or beyond exponential rate of improvement of next-generation hardware.
So one thing that I was hoping you might be able to give some guideposts for is something that I think is people often struggle with getting into chemistry is trying to figure out where these hard problems are. And we saw this in the early days of quantum computing, where people would say things like, oh, simulating caffeine is going to be very difficult on a quantum computer, or THC. Yeah, we all know which student of yours did that. Oh, cool. But anyways, can you give a good signpost for where people should look in order to try to likely run into molecules that are believed to be hard?
Okay, great question. And if I was a better chemist, I might be able to answer it. I tell people in my group that I hope I'm a good theorist, and I know I'm an average chemist. But okay, one can talk about different kinds of strong correlation in a slightly physical way. So suppose you've got a site here and a site there. Well, you can have kind of spin frustration if you have the possibility of upspin, downspin. So there are strong spin fluctuations. That's one class. There's a second class then that one can idealize as strong charge fluctuations, where there's a significant amplitude of an electron hop from one site to another. So crudely speaking, strong correlations live or occur most commonly when you have either strong spin fluctuations or strong charge fluctuations evident in the wave function. And the way you discover this operationally running classical codes is bad results when you don't have enough physics, if you like, or chemistry, if I like, in the wave function.
Yeah, so I think this is a rephrasing of the question that people have been asking since decades, which is, what is hard about physics? Like, where does the hardness come from? And I think we don't know. So I mean, I can't speak to as much chemistry detail as that, but I think a common thing that people say is sign problem. I think that's like a very sort of central belief that when you have these sort of large signed counting problems, quantum computers can do that, but classical computers cannot. So I think that's a feature. But I think that we don't know, and I think that going back to my previous answer, I think the way to answer these questions is to write down models and study them, and that's the way that we're going to get an understanding. And I don't think much of this work has actually been done yet. So
well, one of the things that you put forward with this is actually I think quite difficult. Here I go again. I'm supposed to let you guys talk. But one of the challenges is always to define what you mean by things like a physical set of molecules or a physical set of problems. And I don't think there's kind of like a hard measure yet for molecular systems. So I was just wondering if actually any of you could comment about, when a chemist tells me that my model is unphysical, what does that mean?
I mean, I try to understand their statement, so I ask quite a lot of people. So I think they mean is like, so for example, for Fermi-Hubbard model, like it's a really simplified model. I think that's what they mean. It's like all the models they are studying now, most of them are toy model. So that don't really like model like the real materials. So for example, like one intuitive reason we believe quantum computer can solve those problems, we might say, okay, if one day because like the materials go to ground state or thermalize in nature, so there must be a quantum algorithm which can prepare the ground state or give states. So on one hand, this sounds reasonable, but on the other hand, it's like the model we write down does not really capture the exact materials, right? So I think that's what they mean for it's unphysical.
So, would you like to go next?
I was just going to echo that. I think that I think that's exactly right, and that at least a chemist's view is that the Hamiltonian is given to us, and we should not model it. Rather, if we keep nature's Hamiltonian, then it will reveal strong correlations in some systems and not in others, and that way there's always a link to experiment. So maybe there is a little bit of a sort of culture clash between the model Hamiltonian community and what one might then call the ab initio community, who want to leave the Hamiltonian untouched.
But I mean, like typically, if you take a look at the calculations that people end up doing on, say the nitrogenase, for example, pseudopotentials are widely used, and that is kind of, like not ab initio anymore. Yeah, my pockets suck. So I was just wondering, do you consider that part of the model building part, or?
Pseudopotentials are a relatively mild sin on the scale of the Hubbard-Hamiltonian.
Okay, so I think I'd like to actually just change the question that you asked because, okay, so what would an ideal model be? It would be simple, it would be realistic, and it would have quantum advantage, right? So I think I would actually, out of those three, ditch the realistic one and say we just want to find a model which is simple and has quantum advantage. Like that's, I think that's a good sort of goal because honestly the only way I know how to write down a physical system that has a very solid case of quantum advantage is to sort of embed Shor's algorithm or something. That's literally so.
I mean, from that perspective, right? Isn't it? You can certainly embed the verifier for QMA circuits in a electronic structure looking Hamiltonian. So are we already done?
Yeah, like I think Sandy has a result which can prove like electron structure in fixed spaces. It's QMA hard. So it's like, so one thing I don't really understand, like Robbie's, goal is like, if we want some kind of hardness, we can always, embed to some like reduction. We can say, okay, so for example, like why, I think it's a bit tricky to say like, or to understand like the connection between what we mean physical, right? What do we mean, what's physical Hamiltonian and what's quantum advantages like? So for example, like do you view BQP complete Hamiltonian as physical?
No, so I would say, okay, the only reason why BQP completeness for a Hamiltonian system, okay, so first of all, that's a worst case thing. I would like more of an average case, like an average case system. But the only reason why BQP completeness is actually at all convincing is because of Shor's algorithm. It's because you can embed Shor's algorithm. That's really the only sort of,
No, Shor's algorithm is absolutely useless for that point.
Okay, but what if I say some family is BQP complete, and then you're like, okay, that's helpful to me. That says it has some sort of quantum advantage. If you ask why it really is that, ultimately you're going to be like, okay, if I could solve it, then I could factor prime numbers. That's sort of actually the sort of thing you're eventually going to say.
Factoring prime numbers is pretty easy, by the way.
Sorry, factor. Yeah.
I know.
So I think we don't expect to find factoring in chemistry, but I think we do expect to find some sort of classical hardness, like sign problem or something. And I think we just want a model that just beats that bar, just as like, it doesn't need to look like electronic structure necessarily. I think that's already a pretty good goal, I would say. So that's my...
Yeah, I have something I want to add. Is like, so in terms of finding like quantum advantage, I think there are two. So I think in practical side, I would say all the electron structure, which is chemistry things hard, you can just try to tackle it. But from a theory perspective, I think there is a direction which we not really think hard yet. So I think so far, like all of those kinds of quantum advantage results somehow try to, we are looking for exponential quantum advantage, right? Like, to achieve this, we try to embed something, do some reduction. So I'm wondering, like, I also discussed with some chemists, so we're wondering, like, whether is there any theoretical result about, like, non-trivial polynomial speed up? So instead of doing embedding, so for example, we're just thinking about local Hamiltonian, like on 2D lattice. So if we want to get constant precision, there are some trivial algorithms. So I feel we don't really try to say, okay, based on those structure, can we get any like non-trivial polynomial speed up? So the reason I mentioned polynomial speed up is like, according to my today's talk, like I mentioned, like there's some belief like perhaps it's possible that the algorithm in chemistry is polynomial, although they are better being polynomial. So I feel like polynomial speed up might be a some like interesting direction to explore. Yeah, I think that's something we are not really try hard.
Well, so a question I wanted to ask, which is a kind of a bigger one, is that, if we're taking a look at chemistry, right, one of the big selling points of it is the promise of course, solving hard problems like computing ground state energies and polynomial time. But of course, because of the QMA completeness, we don't expect this to hold in general. And also, all of these algorithms end up requiring us to be able to prepare an initial state with sufficient overlap with the target. How confident are you that the challenge problems that we're interested in looking at are actually going to have a concise enough overlap that we could actually end up running phase estimation on it?
Seem to be pushing us towards the orthogonality catastrophe here. I guess I'm unsure, honestly, but there are certainly results claiming that one can enhance overlap, and it remains, I think, to be seen how those perform on systems of the kind of high dimensions that I think your question is implying.
I want to instead of advertise another direction. So, okay, although so far it seems like, phase estimation is the most popular, one of the most popular algorithm. And I think, also people do a lot of numerics and suggest in some cases you might find good overlap. Although I'm not an experiment in numerics, so I cannot comment on this. But I think, this is not the only algorithm which can prepare ground state. So there are some other algorithms, for example, some kinds of cooling, like some kinds of simulated annealing in quantum case, or like something adiabatic computation. There are a lot of other methods, I think, especially for cooling one, I feel it's more literal than phase estimation, which might be able to, so if there is really a problem about overlap, maybe like cooling, for those systems, cooling will be an alternative approach.
I guess one of the challenges that ends up coming in is that if you're looking at adiabatic, then there's a problem of estimating what the minimum eigenvalue gap is going to be over your sweep. If you're looking at some type of a Lindbladian approach, everything boils down to what the gap is of that in order to be able to determine the mixing time that you'll end up needing. In the end, how can you say much about these quantities, especially when you know that there's very hard computational problems that so the generic algorithms won't be able to solve? If you could, that would be solvable if you could do state preparation.
So in fact, I have I'm going to say something I'm not sure I'm pretty correct, but there's something I think for a long time about like what does guided states mean, right? So so for all of those algorithms, in fact, you use some guided states. So for phase estimation, you require guided states to have 1/point overlap. Mm-hmm. So for cooling, you might also expect some guided states. For example, you want this state in the when we say like the spatial gap is exponentially small, that means worst case hardness. So if you're looking at a classic example, people show that even for low temperature, the cooling can behave good in the same phase. So like it's hard to transit from different phase, but inside the phase it's not that hard. So so what I'm saying is like so in this picture, like the if you want to find the ground state in a certain phase, the guided state would be something inside this phase, right? So just for example, thinking about we want to prepare ground state of 2D EC model, the most simple one. It's a trivial thing, like all 0 or 1. So if you ask, I want to find a state which has 1/point overlap with this, that's exactly this ground state. But if you're thinking about, I want to do some cooling, then like it's just some state which has, most of them are 0, most of them are 1, right? So I'm saying like the guided states intuitively in cooling is different from the guided states intuitively in like QPE algorithm, which seems more natural. So I just want to say like I feel more natural guided states would be something share the similar properties as the ground state, but not necessarily have big overlap. So that's why I think cooling might be a more natural thing.
So, okay, well, I guess a larger question that I end up having, I wanted to raise this to you, Robbie, is, from the perspective of continued quantum algorithm development for simulating dynamics in particular, what do you think are the frontiers in dynamical simulation for chemistry?
In making the algorithms cheaper, or
Hopefully, we usually don't want to make them more expensive.
that's the direction that you're talking about there?
Yeah, making it cheaper.
Yeah.
Price.
Well, I guess my what I presented today was sort of in that direction, with this sort of SOSA framework.
Yeah, but you've already done that.
What's next?
Yeah. By the way, it's a great paper.
I'm not sure. I think we need some smart people to come up with the next improvement. Yeah.
So but I guess a question that I've always had, and maybe you can provide me some insight on this, is that there's been a lot of discussion over the years about solving electronic structure problems, specifically on quantum computers. But quantum computers are often much more suited for dynamical simulation rather than electronic structure. Are there good examples of dynamical problems that the algorithms community could start thinking about?
Maybe. In other words, a great deal of excitement underlies the response of molecules to fields that are strong enough that you can't really separate the molecule from the field, but really should view them as a coupled system. So strong field chemistry or physics is interesting because it can unveil electron correlation in a dynamical light, and will often have something to do with how reactions might be photochemically driven. So that seems like an interesting area to me. I might elaborate slightly that there's been this sort of revolution in tabletop X-ray technology on the experimental side, and that grew up in the physics community but has migrated into the chemistry community. And my colleague Steve Leone and other colleague Dan Newmark have a lab that they sort of an X-ray lab that they built that do generate these fields that are no longer small compared to one atomic unit, and drive chemistry, strong field ionization, high harmonic generation, lots of things where presumably electron correlation has a lot to do with the dynamical response.
So that I have a question on this. Like, that those kinds of problems, like, do some dynamics on ground states or do some dynamics from some arbitrary states?
Well, if the field is strong enough, the state is mixed and a superposition, and so very much then different than doing the ground state.
Okay.
So I guess a question about the complexity of chemistry in general. There's been a lot of work that I've seen on the complexity of ground states. Is there much that's known about the complexity of excited states?
Yeah, that's a great question. So I think there's some complexity about like finding spectral gap, which is pretty hard. Like I don't think there are so many as far as I know.
So I'd actually like to go back and go back to the previous question. Is that okay?
Go ahead, man.
So the question is maybe dynamics is a better target for quantum computers. Is that the sort of claim? So I think that when you try to like find a concrete dynamics problem that has quantum advantage, you run into a difficulty, and the difficulty is the following: is that if you define a dynamics problem that is sort of very complex, right? So it's very chaotic, and you need, I guess in the Pauli path picture, you have many Pauli paths, or in whatever notion of complexity, chaotic. what tends to happen is all of the observables tend to actually sort of wash out and thermalize and sort of become very concentrated and boring. And then on the opposite side, when you have some sort of signal, it tends to be a sort of integrable dynamics problem that it ends up being classically easy. So I think that's a sort of a dichotomy which is sort of what you run into, and you need to find sort of problems that sort of don't fall into one of those categories. And something I am a big fan of actually, which I think is possibly under appreciated. I know people have mixed opinions on this work, but you know, the recent OTOC paper from Google, I think, is actually a pretty good candidate for a dynamics problem that has both a signal and also is very complex. And then they have also a story about how it's relevant for like NMR calculations or something. So I think that's a good candidate, but that's sort of a difficulty that you can run into.
Well, I'm tempted to go back to the last question and say that I think excited states would be a very interesting area for future analysis. There are some recent results from the classical electronic structure theory community that might be interesting to just throw out to you guys just about excited states. So for instance, there is an old, well, this one's not exactly new. Suppose you knew the exact ground state density functional. I believe it is true that every stationary point of the exact density functional is an excited state. However, the converse is not true. Not every excited state is a stationary point of the exact density functional, which hints at additional complexity. But the fact is that is stationary points of the ground state density functional. So when you do a ground state calculation, you're at what should be a minimum in the one particle Hilbert space. When you attempt to do the excited state search, all there is a stationary principle, no minimum principle. So anyway, lots of things change.
So we.
Oh, yeah, I was going to explicitly open it up, but please, everybody, jump in if you've got a question.
I wanted to ask a clarification. So how do you define like a stationary point?
Is that a fixed point?
So this is, the context is this Kohn-Sham density functional theory. So the reference wave function is a single determinant, and the stationary point then is the energy made the first variation of the energy with respect to the orbitals made stationary. And on the ground state, furthermore, that should then be a minimum. For the excited states, a first order saddle point or perhaps higher order saddle point.
And then is the quantity we care about is the energy of excited states or some measurement observables of excited states?
I think the energy in the first instance, as usual, but there are also transition properties that couple the ground state to the excited state, like the transition density matrix is interesting. So that would control, which excited states are optically accessible or which are accessible in a two-photon sense. So the energy is always the starting point, but less so the ending point for excited states, I think.
Cool. Do we have any questions from everybody else? Yeah.
Yeah, so I want to, change of topic. I want to ask about, several speakers have talked about embedding, because as far as I understood, embedding is a great thing because you cannot solve a strongly correlated problem completely on a classical computer. So that's what you have to do. You divide the problem, you divide it up, into a few parts, and to make a smaller, strongly correlated problem that you can actually solve to some kind of exactness, and then you glue all them up together. So I kind of don't get the point why we're talking about doing it on a quantum computer, because the whole point, or the hope, or the hype of this is that you can just solve the original thing and without having to do these sort of approximations that you have to do if you have a classical computer. So that's where I'm confused why people are talking about. Does that make sense? Talking about, for example, embedding on a quantum computer.
I mean, I think maybe like, what if the fragment is too big for your coupled cluster, right? I think.
We just counting qubits here and saying we have to stop, therefore we must embed.
Okay, so in that case, you're thinking about a case where solving the whole thing on a quantum computer is still impossible, but some kind of reduced embedding problem is possible on a quantum computer, but not possible on a classical computer. So it's a very delicate regime, which I'm not. Wait, does that exist? Does this regime exist in applications?
I think so.
I just want to make a quick, answer to that. I mean, I guess the size of what we're able to do quantumly is going to change over time, right? So, right now it might be we want to do something with 100 logical qubits, and then in the future we're gonna have more and more and more. So I guess it's size of what we can do quantumly is not static. So I guess there's sort of has to be situations where it's possible, given that it's going to be some continuous.
Right. It's also
function.
non-static for classical computers.
Yeah, sure.
But hopefully there's a speed up, right? Hopefully the quantum computer is better than the coupled cluster.
Well, couple cluster is not the only candidate, but yeah, that's it.
So Umesh, you had a point?
I have a naive question, which is, one assumes that molecules are extremely stable, because they exist, and so how is there an argument saying that just by directly simulating cooling, that this is not the that this is just not going to be the right way to go? So what's the given that there are all these much more complex methods being pursued, is there a very easy way to see that that's absolutely not the right way to proceed? If you were just setting up.
I mean, I think that I think maybe that is the best approach, but I guess the question is, what do we do about it now? It might be just a case of we have to run it when we get the device. The question is what am I going to work on next? I guess. So, but you may we don't know. Maybe that is actually the best performing quantum algorithm.
So I'm also not a physicist, but this is again someone other people told me. So other people told me for analog simulation, you can do cooling, right? But it's very hard to cool to low temperature. Even you can cool to temperature is also a very complicated concept. So for example, there are some people doing analog simulation from a Hubble model. It's true they can cool the temperature to something, but the effective, the final thing, the final model they get, they also don't know what's the model. So that's what they tell me. It's not that easy to cool down to. So the most natural way of cooling is not that easy to cool down to a very low temperature. That's what they told me. But maybe you know more.
I don't think I do.
But I think it's one thing to cool down a toy model, but if you're actually trying to simulate a molecule, and the molecule is so robust that there are zillions of copies of it sitting around and they are identical, well then surely cooling must be easy, otherwise nature couldn't have done it.
One of the things that's interesting about it is that it depends on the resources that you bring to bear. If you want provable guarantees about the amount of time that it's going to take in order to do it, the best methods that I know of use Haar random interactions to be able to do this. And just to make sure that all the subspaces can always couple, because if you choose any type of random interaction with the environment, it might not have the coupling that would end up causing the decrease that you want. And you can get provable convergence to a low temperature thermal state with this, but it takes time. It's polynomial in the dimension of the Hilbert space. So I think that actually your answer might be yes, but it could take a lot of ingenuity to be able to find the model for the environment that actually does a good job of cooling to the ground.
But, sorry, but just coming back again to maybe I'm looking for the right way to think about it, because naively I'm thinking, look, did nature somehow chance upon the absolutely perfect way of cooling these molecules down, systems down to these particular perfect molecules each time? How could it be that it took so long to produce these molecules the way they are? And so shouldn't it just work if we throw something at it?
Well, again, just like anything else, if you've got a Markov chain and you have a set of random transition rules to it, you're not necessarily going to equilibrate to a useful distribution. The same thing ends up happening if we're dealing with a noisy system, right? We need to make sure we've got the right transitions built into our system bath coupling to allow the correct moves from one energetic state to another, so we can rapidly cool down. If we choose those transitions really poorly, then the system will take a very long time. Now, the question that you're thinking is, okay, if nature does it, then maybe we can end up mimicking nature, and that's fine. But it depends, I think, on your goals. If you want theoretical guarantees, it's hard in some of those cases to do it.
No, I don't want theoretical guarantees. I just want a practical system. So shouldn't we just jump in and try to do that?
I have a question. So, I mean, we heard from Martin this morning that room temperature is below the gap. So these things are sort of in their pure states. Does that change this? That doesn't affect this belief or not? It's the question.
Does that change the question?
Yeah. Well, does that change the hope that these sort of cooling algorithms are going to work well, or it's fine for them to sort of end up in a pure state?
Well, I would assume it's somewhat similar to the question we have with proteins, right? Where we say, look, protein, maybe protein folding is extremely hard in general if you are given random base pairs, but proteins have evolved over time, and if you have those particular base pairs, they just happen to be extremely robust in the way they fold. But it could be that molecules we are interested in have this property that they are so robust that they happen to robustly get down to their ground states and
I think
how do you know what the protein's ground state is if you can't even compute? I mean, proteins are very complex. Are you just guessing that they fold to their ground state? Because it seems like that's a very complicated case of the, in basic calculus you have the local minimum problem, right? So if you've got this physical object that's beyond the complexity, how do you know it's actually folding to its ground state?
That's the belief,
See what I'm getting at? Is that just a belief, or?
I think the issue is not that it's in the ground state, but it's robust.
It's robust.
That you can
Okay.
denature it
So
in
it's
many
in a
ways,
deep,
and
it could be in a
snaps
deep
back
local
into-
minima, right?
Yeah.
Okay.
This is kind of funnel analogy that, protein folding is sort of like falling down a funnel, and that nature has evolved that, and it apparently renders the question maybe not one that we have to answer. But maybe I can try to come back to Umesh's question about the stable, easy systems. So, a stable, easy molecule is one that has a large gap where the electrons pair, and a Hilbert space of fantastic dimension is optimizable classically in a number of steps that is independent of the size of the molecule. It might be maybe 20 steps in a million-dimensional Hilbert space, where if it was a quadratic surface, the termination condition is 1,000,001 steps, right? And yet we do it in 10 or 20, independent of the size of the Hilbert space almost. So in a certain sense, the cases where classical quantum chemistry work very directly reflect that we know how the cooling, if you like, from an arbitrary initial guess to the ground state is extraordinarily efficient in an optimization sense. You know, you've got no right to solve million or tens of million variable optimization problems in 10 steps in general, yet we do. So
I think Anthony wants to say something.
So I think maybe here's one way to try to sharpen Umer's question. So take your fix the position of the nuclear, and this is finally the electronic structure problem. The question is, are there many local minima of this problem so that it becomes glassy? Is there only one, or is there many? Right. The question, if there's many, then we should somehow see a lot of them in nature. So maybe there's only one.
So can you repeat?
Yeah. So let's try to sharpen. So say, take your favorite molecule and pin the position of the nucleus. Right? And this is finally an electronic structure problem. Right? And the question is this guy supposed to have lots of local minima, so it's like glassy, you know, very hard to find, or is it actually just one? Right? And you know, if there's lots of them, then we should probably see a lot of them in nature as well. And if not, maybe it's just there's only one, and then whatever you do, it will fall into that one. Right? So it might be an empirical evidence that there's just one kind of whole.
In the glassy case, also they are very low energy, right? There's a whole bunch of comparable energy. I think that, you know, because we have nonlinear, in principle, there are surely multiple solutions all the time, but I think often there is effectively only one that is low energy.
Yeah, so I think, I'm kind of, you know, convinced, like, it's pretty convincing what you guys are saying. But then, if that's true, then I think, what should we do about it? I think it would be really nice then to find a concrete ensemble or a concrete model where you can say, look, here's a quantum algorithm, you do some cooling algorithm or something, and whatever it's doing is we don't know how to do it classically or something. I think that would be really good progress. Yeah.
So to look for inspiration to the future, like can someone tell me what is the poster child of classical computational chemistry? So like what is the FIMOCO of 1980s or something, where once they figured out the third rung of the ladder from Martin's presentation, then they were able to like, oh, this was wrong, this assumption was wrong, or like this molecule can be made or something like that. Is there like an easy answer?
Well, let's see. I mean, I guess I'm not 100% sure I understand your question, but the kind of aha moment was when people realized that density functional theory could get molecular relative energies nearly as well as coupled cluster theory could for orders of magnitude less cost. And there was not necessarily strong correlation involved, typically not, because DFT doesn't do that, but it was basically the chemically usable results for relative energies in diverse systems that, you know, that are kind of well-behaved, easy in the potential cooling sense that Umesh mentioned.
Okay, well, just one last question then to finish things off. I was wondering if each of you could, could tell me what you think is a cool problem that that you'd like it if more people thought about in this space.
So first, looking at fermionic component, the cool problem I would say just try to tackle Fermi-Hubbard model. Yeah, very simple answer.
Yeah, so I think I've been going on about my answer for the last 3 answers, but to say it again, I think that a really cool goal would be to find a nice model, a concrete model that is, average case, and there's a quantum algorithm that takes an instance and computes something, and that we believe it's classically hard. I think that is a very nice goal.
What's your question?
So why is SYK not this?
Well, okay, so, I mean, you're saying we can prepare a low temperature state of SYK and then measure something. So I think you'll probably not see any signal in the observables of the SYK ground state, I suspect. Like, so the main way that you fail, by the way, when you do this, is that the thing you're computing on this ensemble is actually just sort of boring. Like, it's always stuck to its mean. It's like exponentially concentrated or something. That's sort of the, if you get past that barrier, I'd say you're looking pretty good. Yeah.
Strongly correlated molecules are not unicorns. They're just not that common. And so the computational quantum chemistry community can give you hundreds of strongly correlated molecules or hundreds of geometries of molecules that exhibit strong correlations. And so lots of them are interesting, and some, not all of them are giant molecules. You don't have to look at photosystem 2 to find a great challenge. You can even do diatomic molecules. If you take a transition metal atom and you first bind it to hydrogen, those are almost always easy. And why are they almost always easy? Because hydrogen has one unpaired electron and wants to make a pair bond. But then you advance to oxides, where suddenly you want to make two bonds, and some degree of electronic frustration sets in if there isn't a match between the number of unpaired electrons on the transition metal and the number on the oxygen. Then you go to nitrides, and it gets a little more difficult, and you go to carbides. So these are just walking your way through diatomic molecules. And again, when you get to the species that are stable in nature, strong correlation's rarer, but my wish would be for people to reach out and grab some strongly correlated molecules from us and play around with it.
So do you think that like you could take your understanding of where a strong correlation appears and like use that to write down a nice model and then give it to this community? Like, would that be something that it would be possible, you think?
I think that's beyond my personal powers, but for instance, we are pretty good at analyzing data and identifying criteria that signify strong correlation. Turning that into a model is not my forte, because I'm inclined to stick with nature's Hamiltonian through thick and thin, but I'm happy to pass it on.
Okay, we're at time right now, so we probably should wrap it up, but that doesn't mean you have to stop asking folks questions during the break. So let's thank all the speakers one more time. Oh, yeah. Or the radicalizer in my case. Thanks. Plutonium dimers. That's what I want.